Are they replacing it, or are they? Anyway.
Oh, we're live.
All right.
Hangouts are welcome to the Daniel Krawitz channel. We're going to talk about Turing Completeness today, and I am with Richard, and we have both prepared our notes on Turing Completeness, and well, hopefully we'll be able to teach something that that other people will be interested in. So why don't you start?
Okay. Hi. Yeah. Thanks for having me. We'll dive right into it. So a lot of people, obviously, in this space are kind of interested in whether or not Bitcoin is Turing complete, simply because they want to be able to do all kinds of fancy things that we haven't dreamed of yet. And this is one of the reasons why Ethereum, of course, was created, and one of the reasons why we have so many altcoins. So it's kind of an important part of the discussion about what Bitcoin is, what it was meant to be, and where we're going in the future. To because some people ask, well, what's the point of even arguing about this? So when I first got interested in Bitcoin, part of the reason why I was interested at all was the idea of having some kind of immutable state that could be done globally long term. To me, this was a breakthrough, right? It's almost goes against physics in a way, and that's why it takes so much energy and the mining process to keep this thing immutable.
Well, that's what the Byzantine general's problem is.
Right.
So if we have a solution to it, we might as well maximize the use of it. So
Exactly.
People are, if they don't know what they can do with the blockchain, then you're not maximizing its use.
Exactly. And we have people having endless excuses for every kind of token that you can imagine, because Bitcoin can't do it, or whatever, and it's really taking away a lot of the energy that could be put into making this system. And I believe Bitcoin's like another version of the internet, or a better version of the internet. It will allow the foundation for that anyway. So back in about 2014 or so, actually before Craig Wright came out and said that, I was really excited about Bitcoin being Turing complete, because I had done a lot of analysis on it. And so I made a post in the Channel 9 forums, which is Microsoft forum place. It's kind of a think tank for people that are into deep into Microsoft programming languages and things like that. And I posted a post about Bitcoin being not only Turing complete, but possibly a quantum computer. And I really wanted to spur the discussion about it. And then in 2015, when Craig Wright finally came out and sort of said that, I already believed that was true. And the reason why I've been in computer science a long time, programming for a long time, and I'm really curious about what you can do computationally with different systems. So it was kind of natural to think about what you could do with Bitcoin. It's a message passing system that has this mutable structure, and I've been studying functional programming languages, and I already understood that it's possible to program with immutable structures. It's possible to program with data structures that are immutable, like Datomic, which is essentially a database that is immutable and based on purely functional data structures, is allows you to do time-based queries, and it never deletes any data, right? So
wait. Now that you started talking about functional programming, why don't we define that?
So functional programming would be something, especially purely functional language, would be something that really follows the LAMBDA calculus in this design. The simplest functional programming language would have been Church's first formulation of LAMBDA calculus, and then eventually Lisp came out with McCarthy to build the simplest version that they could possibly, the simplest basic computational machine that they could come up with, which was Lisp, this language that has both the similar structure for its data as it does its programming language. And the back in those days when Church was around, the Church-Turing thesis came around and sort of generalizes computation. it goes beyond what what when we are going to argue about Turing machines, about what kind of computation can be done. Like, you don't need to have it doesn't have to be a Turing machine. It can be something else. And so we but he showed that anything that is based off of lambda calculus or general recursive functions it could be equivalent to you could make equivalent Turing machine. And since he proved that mathematically, and that opened up the doors for us to be able to create all kinds of languages in the functional realm. And so that's the thing about functional languages. If you were to use a purely functional language all the way through, and one of the reasons why it wasn't used in practice for so long, until the last 10 years or so, actually, where people start using it in the real world nowadays, it's because we didn't have a way to really do some of the things that sound pretty difficult when you can't mutate data. So it took a lot of computer scientists over the years to come up with some things that were able to do kind of magical operations, such as the monad in functional programming languages. So Haskell, which is actually kind of even a little bit more different than Lisp, actually a lot different than Lisp, is based off of combinatorics. It's a combinatory logic, based off of combinatory logic, and it has its foundations as well down in lambda calculus as well, but it's quite different. It allows you to write your code without having bound variables, which essentially lets you compose functions much more nicely, and enables you to code in a way in Haskell. They allowed them to figure out how to use something called monads practically in a language, and that was important because it allowed you to do things to control side effects and handle things that to sort of like, instead of like, they do something like this. Okay, I want to sort of express and sort of give people in the Bitcoin community an idea of how you can deal with mutability in functional world. In the case of monads, instead of like mutating the outside world, like touching something and changing something on the outside, what a monad does is essentially takes the entire universe, the context, the environment itself, is encapsulated inside it, and it can do whatever it wants to that. And in order for that, and so the whole universe is within it. So it's going to mess with it messes with the state inside itself, and can pass on that state to another monad, and so on. And so when I was looking at functional programming language and how Bitcoin could be used, and how it's immutable, I was trying to think about how we could design a functional language to communicate or to write programs on Bitcoin, and to solve all kinds of neat problems that nowadays are we're starting to use a lot more probabilistic computing, right? And that Bitcoin could do this kind of thing. So I was super interested in that.
Okay, well, wait. Let me
go ahead.
comment on some of the stuff you said so far.
Sure.
So first of all, let's go over the Church-Turing thesis. So a model of computation, that means an imaginary computer that abstracts away physical limitations. So real computers are necessarily finite machines, but a model of computation is not infinite but unbounded. So we don't put size limits on it, but we don't want to generate infinities with it either. But we define an imaginary machine as if it is infinite, and we don't have to worry about energy and resources and time and so on. We're only talking about the rules of computation. And the Church-Turing thesis says that no realistic model of computation is more complex than a Turing machine, in the sense of being able to perform computations that a Turing machine cannot do. And this thesis is not mathematical, it's philosophical. And it has never been falsified because there doesn't seem to be a way that you would actually prove it. But what our experience has been studying computer science over the past century is that there are various different models of computation that we can imagine that are superficially quite different from one another, but they are also all fundamentally of the same power and are able to
Mhm.
do exactly the same things as one another. So
Mhm.
the lambda calculus is one example of a model of computation, and a Turing machine is another one. And there's another that I'd like to mention called the partial recursive functions,
Mhm.
uh, and these were invented by Gödel. Those are the first models of computation. Um, and
Right.
before computers, the machine was invented, people had imaginary computers that they had written about in math and logic journals. So, next, I wanted to comment on what you said on monads. So I would just like to recommend a book by Leibniz called The Monadology.
Yes, I'm
Uh,
very familiar. Yeah.
okay, great, because Leibniz talks all
Yeah.
about that kind of stuff there, but that was way
Mhm.
before computer science got started.
Yeah.
Um, and as to the idea of functional programming, I would define that as we're trying to abstract a an internal state away. So uh, we want to define functions in terms uh, of states and of transformations between states, but we're not thinking about the instructions on how what we're talking about is transformed. We simply define what the output looks like given the input, and we try to do uh, all computation in terms of explicit uh, rules that transform these data structures, and then we don't have to think about what's going on internally in beyond what we see in the programming code, because the way that the code is implemented in the computer allows us to abstract those details away.
Mhm. Yeah, absolutely. And there's an awful lot of difference, obviously, between what people go on about Turing completeness in theory versus practice, right? And in practice, and people have mentioned this before, Craig, right? One of them, of course, that there's no such thing as an infinite tape, really. Well, there's unbounded, yes. So people use these terminologies wrong, and people also mix up, what a recursive language is versus whether or not a language supports recursion, which it doesn't have to do to be Turing complete, but if it does, then it kind of proves that it is. Um,
Well,
so,
recursive languages, that's a way of defining languages recursively.
well,
Uh,
in terms
so,
of that's where people sort of get confused because when they talk about recursive language in terms of Turing machines, they're not even talking about recursion and that we normally think about in a programming language. It's actually just means that the language that for any sentence of that language, it is interpretable, understandable, recognizable. They actually call it Turing recognizable,
right.
and it can halt. It will halt. It definitely will halt. So if something is a recursive language, then it's something that will definitely halt and definitely be parsable. But when it's and that means it's always decidable. But if it's a uh, if it's this non-recursive language, then it or partially, then it may be decidable or undecidable. depends. You don't know. So some inputs may halt or not. And then there's languages which aren't recognizable at all, and they're not decidable at all. You have no way of telling if they'll be able to halt at all or not. And when Craig Wright was talking about in Bitcoin in particular, he was talking about it being a total Turing machine because every script was guaranteed to halt. And one of the reasons why it would be guaranteed to halt is that because you kind of have to put, right now the way it is. I've tried to think about how you might be able to do something completely internal to Bitcoin period, but there's no like sort of message pump. So like if there was a way right now to create an output that outputted all the state and the next function to be computed, and you were able to like get the next script to execute that somehow, right? And pass that data on with an internal pump somehow, then you could say Bitcoin is completely by itself. The code itself, the way it is 100% Turing complete. But it seems right now that it always needs to have some kind of transaction initiated from the outside, and that's kind of like getting input from the user or anything else. In this case, you have to send a transaction with some kind of fee to get the transaction recognized and at least brought into the mempool before you can do anything at all. So right now, and also, by the way, there's certainly it's not easy to try to come up with a way that it works. But Clemens Lay went through a whole like last fall, whatever. He went through a whole presentation where he showed how you can structure Bitcoin transactions to mimic the tape on a Turing machine, right? And by doing that, he proves that it works. Now, of course, you always have to. The only thing that's missing is like you don't have a way to inside to control what's going on. There's always got to be something on the outside that sort of keeps the pump going. Now, that could be a really good thing because what we want is for computations that require fees. Like if you have this chain of transactions, that can act like a loop, right? It can go and read something from the Bitcoin blockchain and do something based on that, and then have a chain of transactions that go on and on. But you're going to have to trigger it somehow, right? You're going to have to, and if you run out of fees, then you want to keep it going somehow, you're going to have to add some fees. And I think that's actually a good thing. That's actually a really good way to sort of control how computation is going to work versus something like Ethereum, which I always had a problem with the way that they were trying to do it. But when you're talking about like when people are talking about Turing completeness and Bitcoin, though, there's at least a few ways that people have already demonstrated that we're pretty darn sure it'll work. And it's just a matter of somebody finally laying out the code to do it. And I think one of the simplest examples would be to try to do as much as you can. That's really simple combinators or something like that. That already stuff that's already designed around the idea of purely functional data structures. That makes it a little bit easier to understand what it's capable. So I've been working on some stuff like that. I'm not there yet. But I'd be interested in knowing what would people really need to see. Like I guess what they kind of expect would be I could take a program written in Java, right, and just have it submit it and have it compiled by Bitcoin, or compile it and have it submit a binary, have it run. It's not like a computer like that, right? But it is network. And I think that although I don't know if it's ever been proven or anything like that, but to me, I studied neuroscience as part of I never actually graduated, so I ended up working and programming stuff. But the thing is with neural networks and stuff like that, like we don't really understand fully how the brain computes yet and how things like consciousness emerges, right? So when I look at Bitcoin too, and I see what's happening, I see all kinds of emergent behavior, and I find that really fascinating as well. That that it's possible that every network is actually Turing complete, And I want to look. I was trying to find some more information about that and see, what would be the requirements for a network to like that has some activity on it happening. Is it gonna? Does it emerge as computing? Like, does computation naturally emerge? And if you look at like actually a new kind of science by Wolfram, he talks about the principle of computational equivalence, which isn't proven yet, right? But he has a lot of if you read the whole book or try to go through it, there's a lot of good foundations for what he's saying, and it goes back to what you were saying, um, which is that it's a little bit different than what Church was saying. Church was saying, that no real world calculation, any real world calculation can be done on a Turing machine. That's true, but the principle of computational equivalence is saying that even the simplest computations are actually equivalent. And if that's true, then there's some philosophical ramifications to that. But it's kind of like saying, that just doing simple operations, mathematical operations like addition, subtraction, etc., is really just as complex as doing anything else you can think of. And that sounds kind of crazy, right? But we don't know the answer to that yet. But when you look at things like cellular automata, and you look at just imagining the structure of Bitcoin and how it's message passing and building up these things, then it makes me think that one of the simplest things to do would be to actually implement a cellular automata on the blockchain, and you just feed in a couple of fees to keep it going, because really all you need to do is represent the state of this of the living cells, life or whether or not they're alive or dead. And it's interesting, the game of life is really interesting because there's a certain rule that you can plug into the game of life, Conway's game of life, that actually creates a Turing machine, right? And so there's a simple proof. So so imagine if you were to set a set of addresses that represent this 2D grid in this 2D cellular automata, like the game of life. And if it was, I don't know, 0.01 Satoshis, then it's alive, and whatever else is dead, or it doesn't matter. Like, or if it's 0 Satoshis, then they're dead, and if it's 1 Satoshi, then they're alive, or something. Then I don't see why it would be that hard to set up the transaction such that you could go and just have a process on the outside that initializes this, and you create a series of transactions that just reads the current state and decides based off of so-called neighbors whether or not to send a transaction and empty itself and to kill itself, therefore, or to receive like a transaction. So to try and make some kind of controller script to do this, and that's something I've been really interested in doing, and was trying to think about how to do it. So I was looking at how to lay that out, the transaction structure, to try to map that out. But I haven't gotten very far in it yet. I'm still working on it.
Okay, well, wait. Let me go over some of the stuff you said. There was a lot there. So first of all, this idea of a network being Turing complete. I think that you could pretty easily prove that using the lambda calculus, because the lambda calculus allows for variables, and those can be treated like nodes in a network. So if you're making a lambda calculus program, I think that you could pretty easily relate networks to that kind of program. So next, Wolfram, a new kind of science. So I think that book is complete bullshit. And what Wolfram is interested in the Turing completeness of very simple computers. So the way that we define a Turing machine is something that could be rather complex, or it could be something very simple with very few symbols. So what I say here is that there's a finite number of symbols on a Turing machine.
Hmm.
So Wolfram is interested in trying to have as few symbols as possible and still have Turing completeness. So one thing that he found was Turing complete was called Rule 1110,
Hmm.
and that would be simpler to implement than Conway's game of life.
Yeah.
And the way, and I think that Craig already did that because he talked about that in his Future of Bitcoin
Oh,
talk.
he says that Bitcoin is a decider, which is, that's the same thing that I thought so too,
Yeah,
and
but
I agree with that. But in order to really prove it, you want to show some code. I mean, that's what people really want, right? So
oh,
they can talk about it all day, but they're gonna want to see some code,
well,
and
anyway, yes, well, but I believe he says that he has Rule 1110, and that it was working on Bitcoin at some point in the
yeah, I think he
past,
said he had it running. Yeah,
but it
exactly.
got too expensive.
Yeah, it might. That I would really love talking about that and find out, dig into that.
So let's talk about what Turing completeness actually is.
Mhm. Well,
Um,
there's Turing machines, right? But then what they really want is actually the universal Turing machine. The universal Turing machine is the Turing machine that can run any other Turing machine.
no, let me go over the definition of a Turing machine first.
Hmm.
Sorry, I think we need that first. So the Turing machine is the progenitor of imperative programming.
Hmm.
So an example of a real life programming language that I think is most similar to a Turing machine is Forth. And
Hmm.
if you just imagine the way a Turing machine works is you start with an infinite tape. And there's a finite number of symbols that are written along the locations on the
Right.
tape.
Hmm.
And the machine has a state consisting of a location and a symbol. So it moves along its infinite tape, and it also carries a symbol within it that it moves around with it. And the set of symbols includes a blank symbol, and the Turing machine begins where we have infinite blank in both directions, and there's some finite section that is not blank, and that is the input. And the machine evolves by a function which takes two symbols and returns a motion. And motion is how does the Turing machine evolve? So we take two symbols and we get a motion out of it. And the way that we get the two symbols is the internal state of the machine and the state of the tape that it is currently located at. And the possible motions of a Turing machine are move left and move right, and we write a symbol to the tape, or and I what this means is that we write an arbitrary symbol to the tape. So we combine two symbols with this function, and we could get a third different symbol. But we just get something from the set of motions. A possible motion is write any given symbol, any available symbol to the location. We can also read from the location. So that means uh, copy the symbol at the location into the machine's internal state. And then finally, we have halt. And if the machine halts, that means whatever is now on the tape that is not blank, that is what the machine returns. Um, and so if you think of the two the two ends of the data on which the Turing machine is acting as the ends of two stacks, then you can turn the Turing machine into a two-stack machine.
Right.
So eventually, if you go too deeply into one of the stacks, you just end up at the end of the other. So you have to take that into account when you try to think of a Turing machine this way. But the way that we prove that different languages can emulate one another is we just try to think of the simplest way that we can represent, we can emulate one machine in terms of another. So the Turing machine is similar to the two-stack machine if you think of the two ends of the data on which the Turing machine is acting, because the data is always finite, remember? You can think of those two ends as being the tops of two stacks. You can implement a two-stack machine as a Turing machine that is acting on a finite data in that way. So the Turing completeness means that here we go. Oh, I didn't write it down, but it should go here. Yeah. So in order to define Turing completeness, we need to define the computable numbers. And these are real numbers. So they're real numbers that can be defined by a Turing machine. So mathematically, a real number is a sequence of rational numbers that has a limit. So we have a possibly infinite sequence of rational numbers. As long as we can say that this sequence has a limit, then that sequence defines a real number. Now, so the way that we can define a real number with a Turing machine is the fact that a Turing machine can define a function from the natural numbers to the rational numbers. So n to q. Q is what we call the rational numbers. And you just have to have a way of reading the output of a Turing machine as a rational number, and that's not so difficult to do. So, the input to the Turing machine is the number, and any finite sequence of symbols is a natural number. So we just have to think of how to implement the natural numbers as inputs to a Turing machine and how to read outputs as rational numbers. And then the Turing machine defines an infinite sequence of rational numbers because you can put in higher and higher natural numbers, and that gives you later elements in the sequence. So the computable numbers are the set of Turing machines that can define a sequence of rational numbers with a limit. And what we prove Turing completeness. So we define Turing completeness in terms of Turing machines. And the way that we prove Turing completeness in other systems is by showing how these other systems can emulate Turing machines. And yes, we often will use a universal Turing machine for that purpose, because if you can emulate the universal Turing machine, then that Turing machine can emulate any other Turing machine, but that's not strictly necessary for proving Turing completeness.
Right. Absolutely. Especially when you're talking about like these specific sort of subcases of Turing machines, and there's like quite a few of them. If you um, like, there's some weird ones like what, what is it called again? ATM. What is that?
So I sorry, I forgot to say something, but then
Alternating one.
the computable numbers are always concerning Turing machines that halt. So this is an important point in Bitcoin, because if you define a computation that halts as a sequence of transactions in Bitcoin, then you get a computable number, and you can get all of the computable numbers this way. Or I should say, you can get a computable, you get a term in an infinite sequence that converges on that computable number. So you can get any computable number to an arbitrary accuracy. And you're always talking about functions that halt. So if you're working with Bitcoin transactions, it's your job to ensure that the function that you're giving miners will halt, or you have to, because and they'll be happy to continue accepting your transactions if it doesn't halt, but you have to keep paying them if you want the computation to go on.
Yeah, exactly. So yeah, this is like really interesting. But when people are usually talking about this, what are they really driving at, right? They want to know, can I run anything I want? Well, not in its current state. Okay, fine. But in theory, yeah, there's a lot of us that believe that it absolutely could. We might have to change some stuff to it. And actually, they have been. So in BSV, they've added back some opcodes, and they're doing some other things to make this stuff easier. So I'm looking forward to that happening. But if we were to so if you were to implement, like, say, a simple Turing machine, that's what people would do. They say, "Oh, that's great, but I want to run Java on it." Well, so I don't know if that will ever happen, and I'm not sure if that's the goal. But what I am interested in is, can we use it to create new languages and new systems on? And yes, we can. So I think that even if we used an external oracle, it could easily become part of Bitcoin itself. Like, for instance, if you had to use an oracle that acts as just a state for this looping, to keep track of loops, and the oracle, this is something that actually is in Craig's patent. Okay, so they use an oracle that acts as the second stack, right? And I don't think that necessarily cheating, though, because the oracle could run on the same node if you wanted it to. So it's kind of like saying, we're going to add this to Bitcoin to make it easier to use. So some people might think that's a bit cheating, but I have a gut feeling that comes from being exposed to so many different kinds of programming languages and systems, and my gut instinct says that we could probably program anything we wanted to on Bitcoin. We could probably implement anything. I'm pretty darn sure that we can. I'm so darn sure that we can that I'm willing to bet my career on it, right? And so that's what as a developer, that's why I'm so excited about BSV, because when they finally woke up and they finally have this guy come out saying, no, it's Turing complete, I don't even care if he's Satoshi or not. Honestly, I don't. I really don't, because the thing that drove me away from Bitcoin earlier on was all these people telling me and telling everybody else that we couldn't scale and we couldn't do all the things that we wanted to do. They ripped out the future potential. And I believe that, in today's society, computation and data, that's value, right? That's the software and the data is super valuable. And so it acts as the foundation for the value for the network. People would be a lot less will respect Bitcoin a lot more when it's useful to access all kinds of different software in a seamless, user-friendly way. And if we can pull that off, then people won't even notice. You know what I
Well,
mean?
yeah, people aren't really. I mean, I would say it's hard for people to imagine what is genuinely possible with a solution to the Byzantine generals problem,
Mm-hmm.
and people
Right.
are
Open
still
stores, like for everything, right? Like,
they're still thinking in old ways when the Byzantine general solution is good for so much.
yeah,
We
yeah.
should want to find every way that we can use it.
Absolutely. I even went further than that. Okay, so that the Byzantine general's problem or thing is super interesting, and it was also like, to me it was like, because I was thinking, oh, how did they do this? It's kind of like fighting the arrow of time. It almost tells me something about the nature of reality. It makes me wonder about the nature of reality. It makes me wonder about how the universe works in one time direction and why it seems that we only flow in one direction. And it was super interesting because I was reading a post that Hal Finney wrote about years and years ago about Boltzmann brains. You ever hear of Boltzmann brains?
Um,
So I'll just say briefly what it is. Okay, so it's just kind of like this idea that the universe is so full of these particles that pop in and out of existence, virtual particles, and that the randomness of any square foot, take any square foot or square meter of space, that the probability that your brain would suddenly appear, in space, is very small, but it exists. And having such a huge universe and possibly multiple universes over all this time, then the odds that your brain is just this floating brain in space that just spontaneously came into existence with no actual real other, nothing else real about it, is a hypothesis or a philosophical sort of thought experiment put out by Boltzmann. So Boltzmann brains are just these disembodied floating brains in space that just pop into existence. Okay, and Hal Finney was talking about that, and he was talking about the bunch of philosophy related to that, and about the nature of computation. And it's an amazing thread actually, because it talks an awful lot about a whole bunch of different subjects. And in it, they're talking about the arrow of time related to Boltzmann brains, and how it is that how computation kind of really needs the arrow of time to happen, or we need to fix the arrow of time in software to be able to have some kind of continued existence, like a long-term existence. Otherwise, we'll just sort of disappear. Like all our data, our internet, everything else eventually it kind of will just disappear. And so the discussion is really sort of about, like, how do we philosophically prove the nature of reality is or is not this sort of Boltzmann brain. And they start going into, there's a big, huge, long discussion that they end up talking about what one of the guys in discussion, Bruno Marchal, who, by the way, I think is a super genius. Okay, I think he's a super freaking genius, and he's one of the smartest people I've ever read anything from. And he's been he's a computer scientist and a long time contributor to the Everything List, of which Hal Finney was also a major contributor to. And so this is back in the 90s, and it's still on today. But he came up with what's called the universal dovetailer and the universal dovetailer argument. And the way that when they were talking about stuff like that, I swear to God, I really, when I was reading that, in the future looking back, I was convinced that these guys must have made Bitcoin.
well, what
Okay,
is the universal
because
Dove-Taylor argument?
I think that the Bitcoin is an implementation of this universal dovetailer that Bruno Marchal came up with to try to demonstrate the nature of reality, to try to demonstrate whether or not there is actually such thing as free will, to determine whether or not there's such thing as a computer that could be conscious and be able to understand its own programming or not. So there's some philosophies that basically say that like a computer, for instance, could never understand or could never understand its own programming. That it would never be able to understand it. And so there's a group of computer scientists that believe that, and a group that don't. And part of the universal dovetailer is um, attached to or is connected to this philosophy to try to prove whether or not the universe is whether or not there's free will ultimately. And I think it kind of comes down to that. And among other things, there's a whole bunch of philosophy related to these arguments. Like it extends into Descartes and the mind machine problem. So I thought it was super interesting. But the reason why I bring this up is because, well, Hal was involved in it, and it was talking about the arrow of time, and they were talking about computations that were irreversible in time. And this is all stuff that predated Bitcoin. We knew a lot in those days. We were talking about things like, can we make a program that will run at some point in the future, 100 years from now, that will like send money to somebody? So people were talking about that stuff. And so when Bitcoin came out and everything, I thought these guys must have made it. And in that thread too, I thought, for sure that these guys must have made it. There's a guy like Gunther and another guy, Bruno, and then Hal. These guys involved in it. But there were so many other guys that were and smart people that were involved from other groups that were part of these discussions that who knows, right? I mean, anyway, the bottom line is I think that's super interesting. So if people want to look into the universal dovetailer argument, UDA by Bruno Marshall, and some of the stuff that insights into computation, the nature of computation, that's super interesting too. And a lot of it's way above my head, I have to say. Like doctorate, super doctorate level, like.
Okay, well, I think that went a little bit off topic, so I'm going to go back to Turing completeness. I'll just go over
Well,
my
I'm
notes.
just saying the universal dovetailer would be Turing complete, but it's this idea of having this every branch of reality being computed in part. That's part of the idea. That is everything. If you're going to compute something, you branch off every other probability into this subtree.
Oh,
But
yeah,
there's more.
yeah, that's
Yeah,
that's what you have to do in order to maximize the allocation in your portfolio.
yeah. Split your coins and keep them.
Yeah.
Yeah, diversify.
So that's an important thing to think about. And economics, the prices of future-oriented goods are based on computations like that, because people don't know what the future really is. So in order to determine the optimal portfolio, you have to think about all possible futures and optimize over them. So I still don't. I'll have to look up universal dovetailer for later though, because I don't know what that is.
Sure. Okay. Sorry about that. I should have it's just like another way of looking at computation that I thought was interesting, and it's a pretty modern argument anyway. But also that it looked like it was very much related to how Bitcoin is designed, and I think that at the very least Hal probably had some input into use some of those ideas in Bitcoin itself. So I thought that was pretty interesting. But if you want to go back to just what do we have to do to well, Craig's already done it. Craig's already wrote a paper that shows how you can make Bitcoin Turing complete and how it works, right? He's showing exactly what you're showing here on your slide here, right? Where you have to have that Gödel or people in the West call Gödel or what is the constant and successor of projection recursion, right?
Yeah.
So you have to be able to define a certain class of functions, but there was also like some people that showed that all you need is a three-state like two stack Turing machine will do it all for you too.
Yeah.
So you can have a simple one as well. Yeah.
Yeah. Well, but I think that it's important to be able to think about the different models of computation, because and think about how they're related to one another. So that's why I wanted to go through the classic ones here.
Okay.
So as I said earlier, there's sort of three classic models of computation. There's Turing machines, lambda calculus, and partial recursive functions. And they're each related to one of the three main programming paradigms. So the partial recursive functions, those are like what's called logical or declarative programming. And an example of that would be Prolog.
Mm-hmm.
And we already talked about lambda calculus and Lisp, and I compared Turing machines to Forth. So that covers the three paradigms. So the way that the partial recursive functions work is they're a generalized way. The reason Gödel came up with them was he wanted to compile logical expressions about math to arithmetic expressions, and that was part of his proof that there are undecidable propositions in mathematics. So the partial recursive functions are sort of like the compiled code of mathematical logical statements. So you take like the Peano axioms of number theory, and you relate statements in Peano axioms to partial recursive functions, and then you can have statements about mathematics that implement computations on numbers that have meanings about other numbers, because you have this compilation process. But anyway, that's how it got started. But that's not really related to what we're talking about today.
Mm-hmm.
So a partial function is like a function, except that it can have undefined values. So the partial recursive functions are partial functions over the natural numbers. So that's double struck n. Should have written that. Those are the natural numbers, and but values can also be undefined, and this is necessary because programs don't have to halt, and it's hard to come up with a selection of it's hard to come up with computers that necessarily halt. So if you're going to talk about all computers, you have to take into account the possibility that it doesn't halt, and that's why there's undefined values in partial recursive functions. So a partial function is what a computer does, and two different computers can have different definitions. The program looks different, but they can implement the same partial function. So partial function is like what the computer is supposed to do, rather than what's happening internally to the computer. And we build partial recursive functions out of simpler functions. And those are constant and successor. So constant means you have a function that is defined by a natural number, and all it does is return that natural number. And successor means you can add 1 to any natural number. Projection means that you can apply a function to the result of different functions. So several results of different functions. So you can chain functions together. That's what that's doing. And recursion means that you define a function in terms of all values of another function that are less than a given value. And all of these together form what are called the recursive functions, and they are functions. In other words, they're not partial. They don't have any undefined values. And then there's search, and search is the only way of introducing undefined values in the partial recursive functions. And the way that works is you give search a partial function, and search just starts at 0, and it tries every number going up from 0 until it finds a value for which the given function returns 0. And it returns the value which was given to that function. And this can have undefined values because you could give it a different partial function that has undefined values. So if it can't go through all of the numbers until it reaches something that returns 0, in other words, if it reaches an undefined value, then its value is also undefined, because the undefined value represents an infinite computation. So it cannot go farther than an undefined value. And the subset, the recursive functions, those are used in the recursive languages, which you mentioned earlier, because those are the functions that are used to recognize recursive languages. And that's how we ensure that the recursive languages are decidable.
Mm-hmm.
So we already talked about the lambda calculus. So, but I'll just go over I'll go over how it works, because we didn't talk about that yet. So lambda calculus consists of expressions that look like statements about logic, except that they don't mean anything. So they look kind of like how logicians write, but they're simplified, and they don't have a defined meaning. They're just ways of transmuting themselves, essentially. So that's what's kind of interesting about lambda calculus, is that they define a set of partial functions on itself, and all inputs to lambda functions are other lambda functions, because that's the only thing that exists in the lambda calculus. So we have two things. There's two rules for what's allowed in a lambda calculus expression, and those are the definition of a lambda function, and that consists of a lambda and then a variable and then a lambda term. So we can have anything else allowed by the lambda calculus in here. And the other thing we can do is have function calls, and those are just written as two terms right next to each other. And what this means is that we are calling this lambda function with this input. And computation in the lambda calculus is defined where when a lambda function here is called, which is what we're doing here, and this lambda term is the input. What we say happens is this function returns term m, except with all instances of the variable x replaced by the term n. So lambda calculus is just a way of transforming itself. And
Yeah.
you can implement recursion with lambda calculus using what's called the Y combinator. And I wrote out how it works here, but it allows you to call a function with smaller, it allows you to call a function it allows you to define recursion up here, basically, because to do recursion, you define a function in terms of smaller in terms of another function with smaller and smaller inputs. So you can do that with this, but you can also do general recursion. So you can do other things like bigger inputs or something too. So you can get loops that don't finish. You can get non-halting programs with this, whereas you can't by the definition for recursion in the partial recursive functions.
Yep. Okay. So yeah, and that's actually a really good explanation for people. Although lambda calculus, obviously there's a lot of symbols. It looks kind of complicated, and this is why we don't program in it. It's not as natural to read. But
It's a way of thinking about programming. But yeah,
right.
you wouldn't want to actually use it for something. You would want something that's a little more meaningful.
Yeah. Exactly. But if you can like define the Y combinator in a programming language, then it's kind of like one of those things that gives you the proof, right? It's like, okay, I was able to implement the Y combinator, and so now I don't need to have a loop construct or anything like that. I don't need a while loop if I can use a Y combinator, say. So things like Y combinators let you basically construct your own kind of control flow mechanisms. So you can create a loop, you can create a while statement, you can do all that kind of stuff. It's a similar so in languages like in Haskell, then there is no loops, right? There's no for loops, there's no while loops. So they use combinators, just as you said there, and recursion to implement their looping.
Yeah, Haskell is one of the most advanced languages. So yeah, I really like Haskell. I wish it was more widespread and easier to work with, but it's not. It's not. It doesn't have. It's not as useful as. Well, some languages are more useful just because more people use them. So I guess
absolutely, yeah.
Wish there was a little more interest in really understanding Haskell.
Yeah, it'll take a while for people to start adopting it more and more. I mean, I've tried, right? I started learning Haskell many years ago. There's a course online on Introduction to Functional Programming in Haskell by Dr. Eric Meyer, and he's an excellent instructor, I think. And anyway, it's one of those things, like if you don't use it, if you're a professional programmer and your job is 8 hours a day or more, dealing with code, you're lucky if you can get into an environment where they're doing something like Haskell. And there's a lot of it's interesting. There's a lot of financial services companies and banks and stuff like that use Haskell in certain areas for good reasons. So I hear anytime and there's also, by the way, Cardano is kind of done by a bunch of Haskell guys who want to try to formalize all the stuff about blockchains and everything else. And so I thought that Cardano was interesting, but I've lost my interest over time on that, to be honest. What I think is that we see more and more stuff that comes from Haskell that's getting into other languages. Like in C#, you can write your code to look almost like it. So I tend to actually, but I program in a functional style, and I'm mostly in my professional life has been .NET development. That's where most of my works come from, and so C# is usually, but also a lot of C++ as well. But the so for me, it's just a bit. You're right. Like I would love to be able to use it, but I could never convince my team. You know what I mean? Like they're not gonna spend all the time trying to relearn a lot of fundamental ideas, because you really have to kind of forget about what you used to know.
Yeah, I really like what you said there, because I also try to write in a functional style with whenever I program with pretty much. I think that once you sort of learn how to avoid bugs and kind of be responsible with the way that you program, you just naturally want to adopt a functional style.
Mm-hmm.
And many languages that weren't originally designed to be functional have ways of approaching a functional style. And I haven't used C# very much, but yeah, I've heard very good things about it from people who like the kind of stuff I like about programming. And my favorite languages actually is C++, because I think you can write in a very good functional style in C++.
Well, in
C++,
C++11 you can, yeah,
yeah,
absolutely.
and C++,
Actually, you could before too, but it was a little bit choppy.
um, and it has abstractions in it that are every bit as powerful as in Haskell, and they work
Yeah.
a little bit differently. But uh, C++ is is good because it's so widespread. So I
Yep.
think a thing you can do is learn Haskell and then learn how to program like a Haskell programmer in C++.
Mm-hmm. Well, C++11 has lambda expressions, and that opened the door for being able to program in a lot more functional style. Although you could pretty much do anything you want to, it is added to give you the capability to do it. So you could actually literally take if you take a program like I would write with that uses a lot of LINQ and a lot of or RX or something that's using monads, okay, and it's very much this monadic functional structure. So a monad is like a function, but it's a special kind of function. Let's not talk about what that is yet, but right now, but it gives you certain guarantees about controlling side effects and things like that you only get when using pure functions. So if you program your code in this structure and you program what I call monadically, then you get the benefits of functional programming. And inside your monads, you can do whatever the heck you want. So if you have to, something's a little bit too hard, complex, then you can do some side effects if you really need to inside your monad or whatever. But you're not going to have this affect the rest of your program, and that it really isolates things. So I think that's a super good way to program. And one of the things is that you could take say, if you program that way in C# and you brought it to JavaScript or you brought it to C++, you barely change anything. There's a couple symbols that you're changing, but the code looks pretty much identical. So like if you use RxJS, for instance, is like reactive library that uses monads in JavaScript, and you were to use the Rx library in C#, the code looks almost the same.
Yeah, JavaScript is another example of a language that is adaptable to a functional style, even though it's not strictly functional, and
Right.
that's one of the things that that Unwriter likes about it.
Yeah, absolutely. I think if you stick to the functional style programming JavaScript, then it's not a horrible language.
Yeah,
When you
but
go outside, then it's kind of horrible.
I'll add something to what you were saying earlier about Haskell, though. And in order to write C++ like you would write Haskell, you also need to learn how to relate Haskell type classes to the
Mm.
C++ template system.
Yeah, that's much more difficult for people, especially since like a lot of C++ programmers don't even do templates, and still, in my experience, honestly, I mean, so I've worked on really large code base, and um, there's not too many. There's yeah. That takes a certain degree of expertise. So you really have to show people how to do it, and then.
Yeah, well, I would really like to do a C++ course eventually, but I've got too much going on. But that's the
Yeah.
kind of thing I would talk about in that. So I guess I'm almost done with my notes now. So I would like to just complete those now. So next, I'll tell you about computable functions. So we talked about the computable numbers, and a computable function is a little bit different because it's a function over the natural numbers, and it's a function as opposed to a partial function, meaning that it has no undefined values that can be implemented as a Turing machine. And an important thing to understand about theoretical computer science is that uncomputable functions exist, meaning that it's possible to define functions for which no Turing machine exists that implements the function without such that it always halts. And the way we prove this is with the universal Turing machine. Oh, and an important fact about the computable functions is that they are countable, meaning that a function from the natural numbers to the computables exists and is surjective, although, well, I don't want to say much more about that because I'll probably not get it quite right. So we'll, if we talk more about that, that would have to be in another lecture. But the way we prove that uncomputable functions exist is a universal Turing machine, and we can show that a Turing machine exists that can take as it can interpret its input as the definition of a different arbitrary Turing machine and the input to that Turing machine. And the universal machine will return it will return whatever the input Turing machine would return given that input. So that intuitively that should make sense because a universal Turing machine is just like a programming language. So you're supposed to be able to do any program with any programming language, and the universal Turing machine is kind of like the implementation of the programming language. So real quick, how do we prove that the halting function is an uncomputable function? So the halting function is a function that takes a Turing machine and an input to a Turing machine, which is a number, so that's why it's naturals here, and it returns bool, which just means 0 or 1, or true or false. And it says, it says whether the given Turing machine halted for the given input. So that's similar to what we're doing up here with the search function, because you're sort of running through every possible value of another partial recursive function to see what it does. So the halting function is not a partial function. So it's not, it doesn't have undefined values like search does. And it is uncomputable because of the requirement of not having undefined values. And the way that you prove this is you use a diagonal argument to show that the halting function is different from every countable list of computable functions. So that's why it's important to say that computable functions are countable before. Now, if you were taking a math class, you would actually prove these things. And all I've done is kind of done an outline. But if you take a class, you have to go through all of the details about why they're countable and how you construct the diagonal argument. But that's how it works.
Mm-hmm.
And those are my
Awesome.
notes on Turing completeness. So I don't have anything else for today. So I'll just let you can say whatever you have left now.
Well, it's interesting because like when all this stuff was like uncomputable functions and all the stuff about decidability and whether or not something will halt or not, everything was obviously done in order to, back in these days when people are trying to figure out how to build machines to do this stuff in the first place, right? So yeah, it's really deep stuff. Why is it that the halting function is uncomputable, right? Is super interesting, and it really, all this stuff really eventually gets to the incompleteness theorem, which we haven't mentioned yet, right?
Yeah,
Um,
it's related because
the proofs are actually
undecidability is.
the proofs are similar apparently too. So, but
Yeah,
I wouldn't be able to go
the
into it, but
undecidability proof includes the uncomputability proof. It's just that
yeah.
there's a whole nother layer to it that's about interpreting meaning into these computations as mathematical expressions.
Hmm. So in those days, they wanted to be able um, to have mathematics. They wanted to be able to ultimately come up with every possible uh, axiom that was be required by mathematics. So in those days, there's Whitehead and um,
Whitehead and Russell.
yeah, Russell. Yeah, exactly. Bertrand Russell. Sorry,
Yeah.
escaped me for a second there. That they were trying to philosophically show that that any computation can be done by just simply symbolic manipulation, and that that computation was really just symbolic manipulation, right? That you can take a system of symbols with some rules, arbitrary rules, and perform any computation, and that all mathematics could be symbolically represented and therefore could be computed by a machine mechanically. And they were really driven to be able to do that. So they even wrote a book, the Principia Mathematica, and it was, people were at that time, mathematicians were thinking that mathematics was going to come to sort of like the we're going to end mathematics. You know what I mean? Like have the ultimate physical theory, or something like that.
Yeah.
But in
They thought that
mathematics,
they could reduce the mathematician to a machine, a
exactly,
conceptual
yeah,
machine.
right, exactly. And so it's interesting that although logicians like Girl and it came out and were trying to basically show that that could not possibly be done. But at the same time, they came up with all these other concepts that allow us to do a computation today. So they set the limits on what's possible and what's not possible, which is super interesting. But it's church Turing's stuff that I think is also important to, if we want to talk about this going forward, then it's important to also note that like quantum computation and probabilistic computing and different models of computation are kind of covered by the lambda calculus mathematically. Like they have a strong mathematical foundation related to them, and there's a bridge between lambda calculus and Turing completeness and Turing machines, but it may be a little bit easier to work on what we're trying to do from Church's perspective. So I'm not sure, because I kind of I've been looking at it from that angle instead of trying to go from Turing's angle and simulate a machine. I've been thinking like, well, how can I make the combinators, right? Because if I can make SKI combinators, that's only 3 combinators, then it's Turing complete. And for instance, that's also the SKI combinator is equivalent to the Turing complete. If you could do that and it doesn't need bound variables, then it might be easier to sort of prove. So anyway, we could talk about this probably forever. I don't want to just sort of ramble on without structure. So let me just make sure I covered what I wanted to talk about. Yeah, I want to talk about just multiple ways to do it for a second that I thought were interesting, that we haven't mentioned. We mentioned a little bit earlier, like that Craig seems maybe he did with the Rule 110 cellular automata. Then there's also the external oracle loop thing that Nchain put out with the patent, and Craig wrote a paper on Bitcoin Turing completeness. That's using kind of an external oracle for maintaining for like a second stack. But then there's ideas of making payment channels. Then I think that Ryan X Charles talked about that. But there could be other ways. So I think that I hope that people listening to this kind of get inspired to just sort of take a look at things from a fresh perspective, and maybe the approach from different angles, like symbolic programming, register machines. What about rod logic? You know, or they're all computational models. And I think that a lot of times with the arguments that people kind of like were on stage laughing at Craig when he said, I felt for him, right? Because like they kind of mocked him, and these guys are supposed to be like, you know, leaders in crypto, and it's pretty rude for you to their reaction to him at the time. But
well,
my feeling,
they just revealed their own ignorance, and they revealed that they would rather keep their special position than lose it to someone who knows better. So they're trying
yeah,
to
they should have sat back. Should have sat back and said, you know, at least asked how so. I
yeah.
mean, honestly, really, like, it's just I don't get that. But that I would, yeah, I would love to talk about this a bit more after sort of like, you know, absorbing what we've talked about today here, and um, and maybe follow up with something in the future that maybe we can actually demonstrate a couple of these things with the payment channels and external oracle. That seems more easy than anything else. So I would love to try that in the future, and if I get something done, then I'll let you know. But I'll keep you informed. But
Okay, well, wait.
yeah,
I'm gonna close by talking about how what I think the best way of thinking about Bitcoin is Turing complete is, and that is a Planaria node,
yeah,
UNWRITE'S protocol.
right,
So what you can do with Planaria is define a state machine,
mm-hmm,
and the state machine is defined by a history of transactions in the blockchain. And what the result you have at the end of them is some kind of graph that is a
mm-hmm,
subset of the blockchain.
yep,
And you can define functions on this graph in terms of sequences of Bitcoin transactions. And a
mm-hmm,
function that might have to loop through different values, like a recursive function, is just several transactions. It's a
mm-hmm,
new transaction for each iteration of the loop.
mm-hmm,
And you can define transformations of these graphs that are subsets of the blockchain in terms of sequences of payments. And when you do that, you basically have you have functional programming right there, because
mm-hmm,
your graph is a functional data structure. When you work with functional data structures, all that you do, you create, you never delete. You have a graph, and that's the internal state of the machine, and you don't delete any of the nodes of the graph, but you use old nodes to as pieces to make new ones. So,
mm-hmm,
for example, if you're adding elements to a list, you can just take a shorter list and make a new node that points to the shorter list, and then you have a longer list with one new element in it. And you can do any kind of data structure in this paradigm, and then you have functional programming. So the
Well, especially,
Planaria
yeah,
the
if you could.
Planaria protocol is already an implementation of functional programming that people should learn how to use, and it'll be just like using something like Lisp to to um, to work with.
hmm Yeah, this Unwriter's done like so much over the last little while that uh, it would be, it's one of those things where like this stuff kind of belongs part of Bitcoin, right? So it makes it yeah, absolutely. I've been playing around with it myself, and you're right. Um, so if you were to talk about Bitcoin and Planaria itself, then the argument's over, right?
Yeah,
It is Turing complete. We can build whatever we want, period.
yeah.
So if it was, that's one way we can do it, and it works great, and it's awesome. Um, and if it was part of Bitcoin itself, and eventually, who knows, maybe it would be, then people would, what are they going to say? It's kind of like saying this collection of runtimes that we have, because uh, because it's not all isolated on one system, that somehow it's not computing. That wouldn't make sense to me. It's fine to operate in a network environment, was what I mean. It's fine to require more than one node to actually make an operation complete. If it's fine to require more than one transaction, that's not relevant to the argument of whether or not it's Turing complete or not. And I think that's, so a lot of people are saying, well, what we want is to be able to write a script that is like like Solidity, and they're probably not going to get that, and so I don't really care. That's really not what I'm after. So, but we'll
Well,
see
I mean,
what we're going to see. Go ahead.
everything about Ethereum uh, tells us that Vitalik's intelligence is sophomoric.
Yeah,
It's just that there's so many people who can't tell.
yeah. So if I wrote a system that said, like, I where I put some code, all I did was just stick it as text into a transaction, right? And I made it such that if somebody executed that code for me and returned me some result, that I pay them, and offload that computation, right? And that computation gets performed by the system somehow, whether or not it involved any other third party or not, as long as it's like verifiable and everything else, right? Then who cares? Um, so the system as a whole is doing the computation. So philosophically, we could say, that it doesn't really matter if one little tiny piece that you're peeking at meets this Turing complete definition that you're interested in. What we care about is as a whole. So we're interested in bringing, as developers, like, to Twitch developers and everyone else, we're interested in trying to use Bitcoin as more than just uh, a store of value, as a medium exchange. And to me, the idea of exchanging, that's a computation. It's it's transactions that involve a computation. There's some kind of computation happening there when we do an exchange, right? And the fact that Bitcoin is computing, it is doing things, and not only that, right? It has this magical effect. It has this like magical effect of getting people to behave this way or that way, and it's transforming society, right? It's like transforming society. So on a deeper philosophical level, when I talk about like the nature of Bitcoin, I'd like to even think about like how it affects society's consciousness as a whole. It's like this living thing that is drawing people in and getting all their attention, and affects their behavior. And whether they realize it or not, they're part of a computation that's happening. And what I mean is that whether people realize it or not, the value of Bitcoin or what it can do in the future and everything else is being computed right now by the behaviors that people, how we respond to Bitcoin, and what, whether or not we use it or not, and whether it depends on, and what the president thinks about it, and Congress, and all that stuff is being affected by this program that's distributed, that is doing all these things, that is causing all these effects that happen, that aren't, that don't seem to be, that they're more, they're almost metaphysical connections. Of course, there's an actual cause and effect happening, right? Like somebody sees the price of Bitcoin, it makes them feel a certain way, they respond a certain way. They're part of the freaking machine. They're part of the computation. So, I think it's like that Bitcoin is not just a program, right? It's an interactive program. And we're part of that. We're part of that computation. And miners are too. And so when I think about the entire system as a whole, I think that it's kind of almost laughable to think it's not Turing complete, because in some level, the Bitcoin system is all the inputs, it's all the processes, and it's all the outputs. And taken as a whole, it's clearly computing stuff. It's clearly doing things. It's performing operations, and part of the operation that it performs is kind of like it's like a measurement device that measures the value of something. Like when I go to trade something with you, we make a decision about what price to come to, and when we finally make that transaction, then the price is kind of decided. So Bitcoin is kind of acting as a tool to measure the relative value between two or more parties. Or when trades are happening online, it's a way of sort of computing the relative value, that's perceived value. So computations happen like in the Bitcoin system, not just within the script and within the interactions that happen between all these things in the blockchain, but they happen outside off-chain as well. So it's a super complex system and fascinating, and it's the most fascinating system currently in the world that I can think of that's not biological, at least. So there's no end to what we can do with it, in my opinion. But
oh wow, what a great way to end the broadcast. Yeah, I agree with all that. That's yeah, and I think that there will be a more computation as time goes on.
Absolutely. Well, thank you so much for having me on here. It was really great. I hope we get to talk again in the future. And
yeah, great discussion. Nice to meet you, Richard. I'll see you around.
Absolutely, Daniel. Thanks.
See you
Cheers.
around, everybody.
Bye-bye.